Okay, welcome everyone. It's a pleasure to have Ashish Mishra as our speaker today. So Ashish is a postdoctoral researcher at Purdue, and his research interests include programming languages, program verification, program synthesis, and earlier he did his PhD from IISc Bangalore. So today he's going to talk about software reliability and synthesis. So over to you, Ashish. Thanks.
Thank you, Ashish. And good afternoon, everyone. I'm Ashish, and I work with wonderful Suresh Jagannathan. If you get a chance to meet him, do meet him. So today I'm going to talk about your building formal methods for software reliability and synthesis. So at a very high level, the main goal of my research would be set to kind of I'm trying to generate or build or come up with a verified piece of code. And when I say verification, this could be proving any kind of property of the program. This could be validated properties of these programs, full complete verification, functional verification, or other kind of properties like the coverage of the program, etc. And there are various ways to reach this goal. You can get a programmer write program without having any kind of verification question in mind. And then do a post-factor program analysis to try to prove whether this program just satisfies its property or if there is a bug in the program. So the other approach would be to let the programmer be more involved in the verification process and give her richer tools like, let's say, one of the flavors, richer formal method tools like one of the flavors I'm interested in this visual notion of types, so as to write correct by construction programs. More recently, there has been another approach which is becoming very popular, is where you remove the burden of actually writing the program from the programmer. Let her just give these specifications about the programs, what the program should be doing, with some kind of declarative specification, and let some kind of deductive synthesis agent take the specification and translate it into programs. And as a side, you get some kind of verified guarantees about the programs. So based on these things, the work would be very logically partitioned along three different streams of programs. So one is about program analysis and refactoring. But the streams that are kind of keeping me more busy these days are the theory right. And these include the automated verification, where I'm mostly relying on richer notions of type systems. And then there's the speech of program synthesis, where we are doing a lot many more interesting works both in on the two fields neurons. And that's how I will also kind of outline my talk today. That I will be talking one work each from these two domains. I'll be talking first about Cobalt and then about coverage types, and then at the future work I'll talk about very briefly about some of the work you have submitted and other works. So let's jump into Cobalt then. So Cobalt is specification-guided component-based synthesis from effective libraries. This is a mouthful, as you can see. So first of all, there are a lot to unpack into this. So let's first try to understand what component-based synthesis is. So program synthesis, I'm assuming that you have some broader idea of what program synthesis is. You have specification, you want to precise program. But the motivation for component-based synthesis comes from the fact that when we are actually writing programs, we are very rarely writing programs from scratch. Rather, we have at our disposal a large set of libraries based on what framework or language we are using. And as a programmer, we are kind of have some kind of underlying algorithm or some program logic in our mind, and we are using these libraries to kind of hold these things into programs. So the component-based synthesis then kind of take this normal program synthesis idea to the further level, that rather than just taking the specifications, can I also give my synthesizer some kind of representation of these libraries? So the synthesizer has the specification pi as well as the other libraries as well, and then you get to generate these programs. So component-based synthesis is quite kind of popular in the program synthesis world. In fact, many of the languages have their component-based synthesis work published. in various field conferences.
So actually, what is pi? Can you tell me again?
A pi could be any logical specification about the program. So, for example, you might be interested in synthesizing a program which reverses a list, which flattens a tree. So you just give a specification. It could be even simpler that you just say that given two numbers, I want an output which is less than both these numbers. The specification.
So is it one be correct to say that the pi is like a logical formula?
Yes. So generally, the way I will be talking in this talk, it will be some logical formula, but there are other specifications about programs. Input output is one good example. So rather than if the user is not very comfortable with writing logical formulas, they can give it input outputs. So I'm just saying that this is the input, this is the output. But this is some specification about the program you want to synthesize.
But then the compiler would turn that into a logical formula, right? Eventually, when you check the correctness of the program, you're basically looking for a proof that the formula is.
Yeah, what you're alluding to is that if you are going from input output example, there are only limited amount of things you can prove. In order to actually prove something, you have to translate it into some form of logic to verify whether you're right about that. There are different flavors of program synthesis. They are not at all interested in actually proving anything about the program, but for this talk, yeah, you can assume that it's the logical form.
So what is the circle there? These are the libraries you were referring to.
This is some JavaScript library, Blue something, call it Blue.js or something.
Give me a small circle or
The bigger one. It's a bunch of libraries which are going to use.
Oh yeah, well, this is more like representational to kind of bring the audience some actual. So these are all the libraries depending on what language you are. These are OCaml. This is OCaml library. This is OCaml library. This is Haskell library. This is JavaScript. This is Python, and this is JavaScript. This is JavaScript. So. Okay, so this is about what the motivation, but it's very important, I think, to understand how a component-based synthesis problem looks like. So no matter what paper you're reading, you'll always find a component-based synthesis looks like this. This is an example of a component-based synthesis problem. So you will have a set of components or libraries, and generally what you have about those libraries is some specification of those libraries. So for example, type specification of those libraries is one good example of that. You can think of some of the specifications as well, but along with the library, you will also have the query, the file which we saw earlier. So, and for example, in this particular case, given a list library, let's say that the user has in mind to kind of find the sum of the best k integers in the list of integers. And so you can give it a type signature that it takes a function as list as an input and an integer k and returns another integer. But as you can see, this is very underspecified in order to find best case sum. So most of the program component-based synthesis will allow you to refine your queries using some kind of refinement. And input output is one good example of refining a query. There are other ways of refining it using logical formulas, but I don't want to go into that at this particular point in talk. We'll see how to refine it using logical.
So what do you mean by refining here?
So what you are saying is that this represents, this, if you look at the outputs which satisfy this particular type, there could be many functions. So for example, I can take a list, an integer, and I can return the same integer. I can, if it's a list of integer, then I can return any integer. So there's a larger set of programs which this is representing. By refining, you are saying that there are additional information I want to give to the synthesizer so as to prune away some of the things. So this is one way for the user to give the specifications, So this together, the library, the query, and some kind of refinement is called the synthesis problem. And then the task of the synthesizer then is to search into the library some composition of these functions, such that the overall type satisfies the query type, and the function also satisfies all the refinements which you have given. So here, the refinements are input output example, so you just see whether the overall function actually satisfies the input output example. If these were logical formulas, which I could check whether the given function actually verifies against the logical specification.
So is it always possible that you can compose some functions and produce something, or it may be possible that you do not have enough things in the library?
Totally. So normally, component-based synthesis is interesting when you have large libraries, like in hundreds, even in thousands in case of Java at least, or JavaScript. and it is, don't know whether there exists a solution or not to start with. And even if there exists a solution, you have to find it in an efficient way in a larger library. So it's not, to answer the question, no, it's not always necessary that there will be a solution. And in that particular case, you can improve things. Either you ask the user to refine their query further so as to narrow down the search. Although refinement will not be the solution if the original problem does not have a solution, as you can see, because the original problem is a much bigger set. So, but in most of the cases, in that case, the probability syntax just return saying that there is no solution, and most of the time the user has to change the query. So it's not always necessary that there exists a solution in these cases. So the question we ask in, so this is a well understood idea, and basically. So this idea has been implemented in various programming languages across conferences, and for Java, for Haskell, each has its different challenges, but the general idea is this. So the question we ask in this work is a bit different. We ask that what happens when these components of the language do have side effects associated with them. So the general understanding before this, and this has been quoted in the papers, that the current approach of using purely functional things where we are not where the synthesizers are totally agnostic about the side effects is sufficient to also synthesize programs in this world. And the idea was that since we are just looking at types, and types are sound representation of the program, they should be sufficient to synthesize these programs. Unfortunately, that is not the case as we show with this very abstract example continuing on the earlier one. So suppose we are looking at library with just two functions. And these functions have this signature, but rather than working on lists, now they're working on list references. So I'm coming from OCaml words, so I'm using references, think of your language and the choice of what mutability you want. So this, along with the type signature, and so this type signature captures some behavior of the program, but not the complete behavior in some sense. So there is also some semantic, effectful semantics of these functions. So the way they assess the state of the heap available to them. So for example, function f might take a heap in which the reference is allocated, and it requires it to have some shape, phi. And once it gets such a heap, it updates the heap to some other, having some other shape phi. Similarly, function g might take a heap which has a different shape, shown by a different color as well, and it updates it into some other heap state. So what is happening is that these functions, the type only captures the partial information about these functions, and there is this stateful semantics of these functions, which are actually how they are, what kind of heap they expect, and how they manipulate that heap, which is not recorded in the type information.
So I don't understand the type of G, because you say that it takes as input a list reference and gives us output something which is an integer, right? But then you say it modifies or manipulates the heap, like
yeah. So it returns. So a function can return a value as well as modify the heap. Most of the functions can return.
So that is what you are calling as a side effect, like
that's a side effect. So side effects shows up in two. So whether you are modifying the heap, that's a side effect, and whether your requirement on the function, the precondition on the function, requires you to heap be in some shape. So both are called. This is the kind of side effect which shows up, but even the other thing where you are just reading the heap and you want it to be in certain shape, that is also part of side effects, because you need to read at least on the heap. So the problem shows up in as follows. So suppose given this query to the synthesizer, which just knows about this library signature, but it knows nothing about the heap signature, you give such a query to the synthesizer. The synthesizer will go and try to compose these functions together. And this is a sound composition based just on the type, because you are returning a list reference, and I'm taking that list reference as the. Unfortunately, this is not sound if you look at the heap semantics of this, because the required heap state for function G is violated. You cannot compose these two functions.
But this problem is even the earlier example. The reverse you could have removed and it will be the same answer. So this kind of degeneracy that just a type composition is not good enough, that existed even in the functional setting. Because this, for example, the revert function you could have removed and it would have.
I think your argument that the type is not capturing the complete specification is true even in the functional setting.
Yeah.
But the program which you generate, so for that you need further refinements.
Yeah.
And here as well, but that refinement is not coming on the output values generated by this. So remember,
but on the
heap state. So you're right. So any synthesizer, you are exactly right, which has to generate sound and a solution that you rightly pointed out must take the change in heap state into account. The other way to look at it is that these functions which you saw earlier, they have these kind of protocols associated with them, the way they must be used. So sometimes it's easier to think in that way. And these protocols are stateful, so your synthesizer must be able to reason about stateful protocols as it tries to compose these programs and try to generate solutions. Now, to come to a question like what the difference between a purely functional setting and this particular setting is that you grow up the space of the programs you have to search. And the reason you grow the space is because earlier you were just looking into these values generated by functions, and being purely functional, they haven't kind of return the same value. But now the heap state is possibly unbounded. And doing a search in the heap state is basically a night search in the heap state is not free. So this is the requirement from the synthesizer, and this is the challenge in doing this in an efficient way. And so that's what the kind of high level motivation of what this paper is trying to solve.
So is the heap the only meaningful side effect you have in mind, or are there other side effects?
There could be others, but the approach, so for any kind of side effects you're looking for, let's say non-determinism or let's say exception, if you can model it as a specification in a specification language, the same idea which apply here will apply here. But you're right, we are in this work, we are just looking at heap of some kind. But majority really applies, but we haven't looked into it. I think really could be useful if the Haskell community has a lot of different kind of side effects. Other than that, I think most of them are dealing with state effect. So good. So a lot of abstraction now. Let's try to look at real and some kind of realistic example. So here is a query or a mutable table. So a table is a mutable list of strings. Basically, think of a list of strings, and you can modify these strings. And so you have a library for this table, and rather than giving the types of methods, I'm now giving them the English name. But one thing important, so this also has another kind of data types like pair, which is a pair of float and integers to make it a string. But let us assume that the library writer has a uniqueness invariant in their mind, and that uniqueness invariant is maintained by protocols associated with the way this function could be used. For example, the add table function acts as string. So add table takes a table and a string, and it only table reference and a string, and only adds a string into a table if it's not already present. So that's one of the kind of constraints which we saw earlier when we have blue heap and this is an example, blue heap and really. So similarly, there could be other function like str, which always returns a fresh string. So this is another kind of side effect, because what it's saying is I always return a fresh string given a table reference. So I must know what is there in the table in order to kind of find out like I'm always returning new thing. So even with this very simple library, so suppose we have this such a library with each and then average length, basically the other two functions like size table is returning the size of the table, which is an integer, and average length is returning the float value. So the query, now given these kind of effective library, the queries user have in mind in most of the cases is also effective. And that totally makes sense, because when you as a user, when you know that you have the state which is carried around, you want to synthesize a program which manipulates the state as well along with generating some values. So let's say the synthesizer, the user wants to synthesize, add an increment function, which basically has the following signature. Say that I take an input, table reference, and a string, and it returns a pair. So basically, it has to return a pair of float and integer. And to give the side effects or to give the effectful information about the function is trying to synthesize, here I have used this requires and ensure clause because a lot of people understand this better. But think of this that you are saying that I don't know anything about in what context this function to be called. But only thing I know that is that the function should ensure that in final keep state the table size is incremented by 1, and whatever string I have is inserted in the table. So I don't know how to come up with this function, and I have a library which is much bigger than this library here for the sort of understanding. I have just typed many inputs. So this is a kind of exemplifying the kind of queries they have. And now let's, if you just pass this query, and this is a
not to satisfy.
Sorry?
This might not be satisfiable if S is already in the.
Yeah. So if you pass this query, so this is kind of more practical experience, empirical evidence of that. That if you pass this to a synthesizer which is not aware of this, one of the synthesizer at least synthesize something similar to this, where it just tries to add S into the table and take the average length inside of the table and return the pair. So this, as I said, Y is the property, uniqueness property of the functions, and the reason is that what if S is already in the table. So that simple looking query, the correct solution is much more involved in this particular case. So the synthesizer has to look into both the cases when S is already in the table. So this is the solution, let's say, generate. So first of all, it has to split the control flow based on current context and the specifications of the function. So it has to find, it has to make the decision that it needs to split the control flow because S might be in the table or S might not be in the table, and the precondition does not say anything that about that. The second important thing is for this particular case now, when S is already in the table, it cannot directly take the average length and the size of the table. The reason for this, even though it after just taking average length and size, it can create a pair of float, but that won't satisfy the post condition. Because remember, the post condition has two parts, that the S is in the table. So definitely S is in the table, S is already in the table, but the size, it also needs to add one element into the table.
But that it could do, right? I mean, there's nothing there saying that the return value has to do anything with the size. So it could in principle return the original size and average length also, but then just add the fresh string. So this the x1, y1 could be computed before the fresh string, fresh str column. And that would satisfy the requirement.
Yeah, you're right. That will be a correct solution to this. So that brings up a very interesting point that most of these synthesizers, with the synthesizer program, the synthesizer program is as good as the specification you are giving. If your specification is as strong the specification you give, the better kind of coinciding with your intuition it will be. Now, as we'll see later, in the sense, giving more and more intuition to the synthesizer should make the synthesis tasks easier, but it doesn't make the synthesis tasks easier. I'll talk about that in one of the future work. It made the synthesis tasks much harder, in fact. So, but in this particular case, as you pointed out, if you just reverse this order, basically, if you add to the table later, then even that is correct. The only requirement is that you always add a fresh str into the table and size it. So the second thing is that one you have to split the control flow. The other thing is that you have to push this information that you need a larger size into the synthesis process. You cannot ignore that. And final thing is that once you know that you are here, how do you know to make a call to fresh str? There are multiple functions which could be invoked at this particular point, and you have to make a decision that you take it from this particular context to a context where your post condition does satisfy. So that brings to the enumeration process of the synthesis, that you have multiple choices and you have to basically make a search in those function libraries. So three things. One is that you have to be dependent on the goal. You have to know that you need to split the control flow, and you have to do forward enumeration in an efficient way. And so that's what Cobalt actually does. It solves these three problems to get to the solution as we saw.
So what do you mean by the forward enumeration?
By forward enumeration, I meant that at this particular point, there are multiple functions you can call. But there are some functions which will take you to the solution, and then there are other function paths which won't take you to the solution. So doing a naive enumeration and searching won't be very useful. So you have to do a forward enumeration, but in a smarter way. That's what is required. So goal-oriented search and then enumeration in a smarter way. That's what we do. Other than that, this control flow splitting, I think, is pretty standard now in the synthesis world. People understand it very well. So before I go into the overview of this, I want to emphasize that Cobalt comes with a specification language. So from the earlier slides, it's quite understandable, I think, that the synthesizer must be aware of the effectful semantics, and there has to be a way to specify those effectful semantics for the libraries as well as for the query. So the specification language in Cobalt has this form of precondition and postcondition. Now, if you're aware of Hoare kind of in Hoare-style reasoning, it's natural to kind of come up with this pre and post condition. And what the specification language we have is something called as Hoare types, which is exactly a type analog of the Hoare reasoning. So it's just a type system to reason about Hoare logic, reason following the Hoare logic. So that is the specification language. But once you have given these specifications and elaborate specifications, there are three components in COBOL. One is backward synthesis, the forward synthesis, and the CDCL. So the backward synthesis is goal-oriented search. The forward synthesis is just the enumeration so as to avoid these unsound compositions, and CDCL is basically going for better enumeration. So let's see how each of these work. Very in some detail. So the backward synthesis is interesting because what it does is it tries to use the underlying principle of weakest precondition reasoning in the verification world for the purpose of synthesis. So what I mean by that is that it just starts with the post condition. Remember, we needed the goal to be included in our synthesis procedure. So it starts with the post condition queue, and it tries to look into the library to find the function f with pre of f and post of f as the specification of function f. Think of a function which increments is, in that case, pre and post will be that it takes any integer, and in the initial condition it has list has size 1, and in the final condition list has size 1. And it tries to do the following check, which is saying that is it able to prove that given just the precondition of the overall query and the precondition of the function can prove that the post condition implies Q. So what it is trying to say is that while trying to synthesize this single straight line program, it's trying to find out the last piece of function call before it reaches the goal. And while doing this, what it is doing is it's trying to take this post condition and pushing it further up. So that if there is a function such that its specification is sufficient, it can directly make the call here and find a solution.
But P might change. I mean, like as you go through the program, if P holds at the beginning, it need not hold just before the last.
Yeah, but when you are doing backward synthesis and you haven't looked into the context at all. So
right now you're trying to find a one-step solution.
No, you're not trying to find one-step solution. You are just trying to find one step in the initial condition, and once you have find that, then you update it to the weakest precondition as a new post condition.
Okay.
But you don't know whether you are going to reach the initial precondition.
Yeah, maybe you don't know. So depends. So right when you are doing backward synthesis, you don't know anything about it forward. What kind of program can come there? So what you are relying on is that is there sufficient expressive specification in the libraries, which allows me to make these decisions just by looking at their specification. And based on that, only you will do the forward enumeration. Because remember, if you still haven't started the forward enumeration, and whenever you suppose at this particular point I call the forward enumeration, so this will be the new precondition which you will post condition which you will transfer it to. So if you assume that in this particular case, at least this is true, and based on that, I'm saying that if this is true, then based on this thing, this must be true.
So why should P play a role? It could just be that I want some smaller set of conditions which imply pre-F, and such that with that post F implies Q. So why should P play a role at all in the backward?
Because if you just remove this P here.
No, not P. The P was the beginning bit.
Yeah. If you remove this P from here, and if you're just looking at pre of F implying the post of F implying Q, there must be bracket from here to there. What we're saying is that I don't know anything about the context. All I'm asking is whether the specification is strong enough to prove that the function call implies this. But the user might have given some additional information as well.
Yes. So what I'm getting stuck.
Yeah, what we're saying is that rather than having P here, why not have P and some additional formula implying pre, and then I can.
Or P might just change, right? Because this is so this is what I'm getting. So just before I apply the last step, P might no longer hold. Because P is a precondition that holds at the beginning of the sequence. So this whole new to T sequence has to be synthesized, and F is the last step in this sequence. So P may not hold just before F.
Yeah, you're right, but at this particular point, what's happening is that you are assuming that I want to use the information available.
Okay.
And based on that assumption, I am making this choice. The more stricter check would be that just P implies F implies post implies Q. And that will be a much stronger check, which will always hold. You're right about that. No matter how the P changes, I'm just looking at the post condition, precondition, and the post condition. But this also allows you to look whether if there is a solution which you can directly get. So we don't want to lose those solution if there is a one-step solution directly.
So this is about one step solution. Okay.
I think the paper, if you look at the paper, there won't be this P in there. I think the paper does not have the P over there because it's also not general. So okay, so at this particular point, what you want to do is you basically update the post condition to weakest precondition on this, and you keep finding these weakest preconditions as you go along. And unless you have reached to a point where P directly implies the weakest precondition, I think this is redundant. I see your point. This is what I added in this wire. Okay, so but most of the time, as I think Ashish was saying, you might not need to reach to this solution. So yeah, that's why this was not earlier in the slides. This is a new addition. Yeah. Okay. So what will happen is that in most of the cases, your synthesizer can make some progress and then get stuck. It couldn't find any more functions. So at this particular point, rather than throwing this solution away, you create a new query and you do the weakest precondition for this particular part and transfer it over to the forward synthesizer. So what backward synthesis did was basically try to push the information into the synthesis process as well as make the task of the forward synthesis smaller. So you have synthesized some program, assuming that will lead to a solution. It might not lead to a solution, in which case you have to backtrack and do some other stuff which is there in the overview figure. But
so how is it assisting the forward synthesis thing? Like you start from the backward, but then you may not get anything. I mean, you are trying to move forward like with your post and precondition, but then you find that you might get stuck. And then you are saying that you might give it to the forward synthesis and it reduces the task of the forward.
Yeah, because
that part I don't understand.
Because if your solution, let's say one of your solutions was to find a program of size 3 or 4 or 5, then your backward synthesis might find a partial solution of size 2, let's say, and the forward synthesizer will now have to find a program of size 2 or 3. Out of 5, only 3 size. And every size step is a costly operation because there are hundreds of libraries and you have to do enumeration into that. So as we'll see empirically as well, but even from the understanding perspective, I think the way it is aiding the forward synthesis is that it is pushing this information much closer to the source condition P, and B, you have to synthesize smaller programs as you go down.
So, but if it gets stuck somewhere, then will it be possible for the forward synthesis to actually synthesize something, or
yeah, because
it gets stuck, right?
Yeah, because you are building weaker. This weakest precondition ensures that you are building larger and larger. So if there was a solution which you could have found, this is much easier than that because now you are saying that this is the weakest precondition you should be here with in order for you to find a solution. So maybe in the forward, if you just do the forward synthesis to start with, if you can find a solution, you will also find a solution for this because by definition, weakest precondition is saying that there is a solution. This is the weakest of all the preconditions which you would hold by just taking this particular part.
So let me address, like at what point do you stop the backward synthesis?
Yeah, you stop the backward synthesis when you couldn't find any more functions to call. Or you have a backward synthesis limit because these are depth first search in backward way, so you have to give a backward depth. So, but empirically, we never had to give a depth for the backward synthesis. The synthesizer was not could not take this to larger length, and the reason it could not take to the larger length is because the condition it has to check is very strong. What it is saying is that that your specification is so strong that they are alone sufficient to prove this thing, which does not hold because as you build larger and larger context, some of the conditions do hold which don't hold until you have that context. So I think is it okay. So the forward synthesis is I think by now it would be clear in the mind that what it is doing is finite depth forward enumeration. Why finite depth as we discussed? Because these are unbounded. The possibility of the length of the programs you can enumerate is unbounded, so you bound them with finite depth. And the task of the synthesizer here is
I have a question on the previous slide.
yeah.
So when you say you stop, then how is it possible that there is a forward path that goes to that state? Why didn't you find the same path going up?
Because you haven't built, so you are just using the precondition P here, or maybe even if you remove this here, you don't have any other context here which allows you to prove to prove the post condition. So here's the example. So to answer your question, so let's say that you couldn't find this particular path. So you can just make a progress still here. What we are looking here is a single function such that this post condition implies this weakest precondition.
Okay.
That might not be true, but what might be true is that given this precondition and a sequence of function calls, you reach to a state such that given that particular new context and the precondition on the function, you are able to.
So far, P has played no role basically.
And
So far, P has played no role, and
Yeah.
forwards.
yeah, so as you build large, so one good example of this, there could be two different variables, x and y, and your function in the backward, you are just looking at variable y, and the post condition has both variables x and y. So unless you have found a function which have also implemented x along with y, and there is another function maybe which has implemented y, only then you can reach to this particular state.
Okay. Then why not, so why can't I do the same argument in reverse? Suppose I start searching from the top. Then I would not be using Q at all. So maybe I stop somewhere and I cannot make any progress because I don't have any progress part two. So why would these two things meet?
So your question is that if I start from the top,
You get stuck somewhere. If you start on the bottom, you get somewhere else, and there is a portion.
yeah. So in that particular case, so remember this figure. There is a possibility that your point is that if I start from the back and then I start from the forward, it might be the case that the forward does not take me to the solution which is there. But the argument is that if that is the case, then you can go with the earlier forward backward synthesizer, backtrack on that, and then again try a different backward choice. So the idea is that you are starting from the goal and you have made some progress. Whether that there is a path from the initial thing which takes you to that solution. If it does, in most of the cases, it aids the forward synthesizer. But if it doesn't, then you have to backtrack on the backward as well, because these are searched from the backward side as well.
Sure, but why would there be any way to get something? Like, so far what I understand is when you're doing backwards, you're forwarding P. When you're doing forwards, you're forwarding Q. Going forward.
No, we are not forwarding Q. When we are doing forward, we are taking this weakest precondition. Basically, this is I think which I was not able to convey. We are taking this weakest precondition, given the Q and this function forward. So if the weakest, if Q was, say, let's say, incrementing the size of the table, the weakest precondition will express this just looking at the semantics of the function and the given post condition. So the weakest precondition is dependent both on the post condition as well as the function you're making.
So the forward synthesis phase, whatever it would be, will have to take both the first and the last thing, like both the pre and the post into account, unlike the backward. So the backward thing in some sense is not taking the precondition into account. Additionally, the forward synthesis process, whatever it is, will take both of them into account to find a.
No, the forward synthesis will again do an elaboration and assume that and hope that it will reach to a solution. But it's not that the backward information is totally lost on the forward synthesizer. The forward synthesizer has a new post condition, which includes this information which you have in the backward synthesis.
Okay, so is it true that if there is, suppose I did not have any backwards process, is it true that the forward process itself is powerful enough to find the
yeah, I think if you have unlimited time, since you are doing an enumeration, and if you keep on doing, let's say you are doing a breadth first search rather than a depth first search, your forward synthesizer will eventually find a solution if there exists one.
Okay, same question. If I don't have a forward process, I only have a backwards process. Is it true that I will always find a solution?
Again, yes, if you are doing a breadth first search, you will
No, that's
not true. That's not true.
because you're expanding the.
Because in the backward process, you don't know about the initial context. So there might be a solution that becomes true in a new context, which was not true earlier when you don't have context. So I think what is missing is that as you go into the forward thing, so as you go into the forward thing, you keep on building this larger and larger preconditions, strongest post condition, using the strongest post condition. And something, so let's say there is this new precondition. Under this constraint now, your post condition might be true, which was not earlier true just in a much smaller context. So the second question answer is no, but the first question answer is yeah, forward enumeration is able to will be able to find a solution if there exists one.
No, actually, no, I'm also confused. I think the backward thing also should work because then it will be so. This weakest precondition, I thought the definition is that it's the weakest.
Yeah, it should hold.
Condition on the pre which implies Q,
Mhm.
which both implies which implies pre in such a way that the post of F will imply Q.
Mhm.
Is that if that is the definition, then the backward thing also should have.
No, but it's not always necessary that the backward thing will always be this, because you might have in the weakest precondition, let's say a conjunction of things. And every time you're looking for the next function, you're looking for a function whose specification is strong enough to satisfy. Let's say you have a conjunction, weakest precondition is A conjunct with B and conjunct with C.
Mhm.
Now, you might have a function which just satisfies A in a single step. But earlier, there might be another function which might have satisfied B, and then there might be another function which might have satisfied C.
Mhm.
So,
Okay. Okay.
so I think if you have some engineering effort where you can take it, even if your formulas are such that you can always partition them into even a formula, you can always partition them into some kind of disjoint things, then I think your question to answer will be yes, even the backward will find. You can always just make it disjoint and you can look at functions in the disjointed formulas.
What I don't understand is why is there a difference when going forward and going backwards? In my head, it should be the same. If you're exploring all possible, I don't know what you call them, but particles from your library that take you down a path in a depth-first way, then there should be no difference. If you have a graph, you can search on the forward edges or the backward edges. There shouldn't be a difference.
Yeah, I think the difference is coming because even though it might be, even though theoretically, if you have a context, it might be, when you're reasoning, if you have context, you might be able to prove the post condition just using the latest condition. But finding out the context, what sequence of function calls you need requires, is not, I would say, given the weakest precondition and the post condition, how do you break it into sub-problems so that you can build the. So synthesis is a much harder task in that sense.
No, but I have infinite time. I can try all possible ways to break it.
Yeah. So now you know. So now if you come to that you have infinite time to break those things into disjoint components, and it should also be the case that your formulas are breakable that way. So for example, there might be a sequence of function calls which you can do this particular thing, and there's no easy way to kind of break them into sub-formulas which are disjoint in the sense that there are different function calls which can fit you there. But if you can try all possible ways of breaking a formula into sub-formulas, such that each of those formulas are disjoint and capture some function calls in the behavior, then I believe. Yeah, so if you can do that, if you can always take, so let's say you have separation formulas and you know that there are different components of the formulas and each of them are independent of each other, then you can, I think that is the general case of this. Then you can right away break them, take one part of the separation formulas where P star Q, you take one part just Q, push P into the forward, in the front condition, and now you can search for all further functions with just Q. And then now you look at P and if you, so I think that's the catch, that when you are working on states, you don't know whether each function is making call to a disjoint set of objects in the heap. If you can prove that every function in your library is working on a disjoint set of heaps, then you can define a separation thing and you can always break them into formulas.
We will continue special language. You go ahead, I think you're short of time, so.
Okay, I think. Sorry. So I think So this is what you do in the forward synthesis, but so there are two things to notice here. So this particular check is much weaker, and there's much more panning out in the forward synthesis. There are much more functions you can make call to, and that's why even empirically, if you look at this kind of synthesis, at every step there are a lot many possible options to try for the forward synthesizer. So what happens in most of the cases that you don't find a solution right away in the forward synthesis in a given fixed amount of time, let's say. And depth. So what happens in most of the cases is you can make certain progress and then you get stuck again here. There are different reasons for this getting stuck in the forward direction. And either you have exhausted all the functions which could be invoked in this particular physics, which is again empirically which is very kind of a real event, and also critically because many of the functions have precondition as true, which is very general, it could be applied in the context. Or you have these the maximum depth of your depth first search. So basically you have a truncated backtrack. So this is normal backtracking. But the problem is when you are working in these kind of functions with side effects is that the synthesizer spend a lot of time
When by functions exhausted, I mean you can apply one function also the multiple times, right? So there is no applied bound on the depth of the
It could be that
The pre-condition.
preconditions of the functions might not hold once you apply them. So it is very much, you're right, it is very much function dependent. If your precondition of function is true, you can keep applying.
that condition in the area is not solved, but if you solve it, it's not a problem.
Okay. So what happens is that as you backtrack, as the synthesizer backtrack goes along other parts, there are a lot of fun. So this is coming from experience again that there are other parts which are actually leading to kind of failures. And many of these failures are similar failures in some sense that there is a possibility of knowing something about this particular path and then avoiding this other path. So that's one of the noticeable thing about this, that while doing this kind of enumeration, you realize that there are a lot of failing exploration happening in the synthesizer, but many of these failing exploration have some kind of logical relation between each other. That is, once we have explored along one particular path, we can avoid some of the other similar failing paths. So that is what the idea from CDCL is, and it comes from the fact that what you want to do is you have explored along a failed path, you want to learn something about that failed path so that you avoid exploring some of the paths. So in order to understand CDCL, I will just release the query quickly. So this was the original query, and we are looking into the branch of the query when that's what already in the table, and this also gives you a much more picture. And in this particular branch, remember the precondition now is the true condition of this, that is S is already in the table, and the other things are exactly the same. So let us try to visualize how the enumeration, some form of enumeration which is happening in the synthesizer. So, and let us say that we have a finite depth of k is equal to 5. We are only going to do a depth of search with k is equal to 5. And for understanding, we will not look at the exact function plots, rather what we look at is these kind of abstract nodes like F0 and F1. So initially you are at node F0, which is the starting point, and you have this condition available to you. The synthesizer, let's say, tries to make the incorrect unsound thing, and the forward synthesis won't allow this particular thing, so it will get stopped at this particular point. So it tries another choice, and let's say, without loss of generality, that it is able to make some progress to k is equal to 3, and it still haven't found a solution. So we are looking at those cases where we actually go along a failing path and then backtrack. So that's why, suppose we haven't found a solution at k is equal to 3. Now at k is equal to 4, what might happen, and this could happen earlier as well, but you're making a call to, let's say, a function like clear table, which could be called in any context. So that's why it is.
So maybe a reason. Did you say a bit about like why the forward the forward direction will not allow that to explore further?
Yeah, because look, the precondition on this. So I will do this.
Conditions are very important.
So add table requires that
So
it's not in this.
In this particular branch, your precondition now is that S is already in the table.
Nice.
And the add table requires you that S is not, this particular S is not in the table. So unless you give me a new S, I cannot add it to the table. So at this particular point, so you get to the clear case. Now, when you come to the k is equal to 4, at k is equal to 5, there are multiple possibilities. Some of the paths won't be allowed again, but there are other paths which could be taken, but you cannot make further. So this does not give you a solution either, but you have reached the maximum length, so basically this is truncated. So you are doing the exploration and you get two kind of cases that some of the paths you can't take and some of the paths get truncated. So overall, such nodes, there exist such nodes where no further progress is possible, as we saw, and we call them as case stuck nodes. So basically, given a value of k, they are stuck in the exploration process for given. Yeah. So this particular one, rather than just returning and backtracking, we store some information about that particular node. Basically, what we store is the strongest force condition for this particular branch, which takes you to this particular point, and we also take a disjunction of all the truncated precondition of all the functions we have truncated. We are trying to keep track of in what context we reached and what are the things which we have to truncate because of phase equilibrium. And at this particular point, it backtracks, and without loss of generality, let's say that it backtracks to some internal node F5, and it again sees a clear table function call. Now, the reason we are having the same function call, it would also work for other functions, is because when the function calls are similar in the libraries, they're more likely to be equivalent in the evaluation. But just looking at the syntax of these function calls that they are same function, you cannot avoid taking that particular path because the context might be different in this particular case as compared to this particular case. So normally what will happen under clear table, multiple things would happen. You will again find some paths which you can't take. But there might be some progress which was earlier not possible under F7, you might have that possible under F10. Now, there are two conditions possible. Either this further progress leads to a solution, but in this particular case, let's say, does not lead to a solution, you again get truncated. As a result, you get a new stuck node, record that information. And overall, you find that your F9 is also case stuck. So the question is, can we use this? So rather than just going here, the question is, can we use this information which we actually learned about F7 to not take this particular path and making this decision at F9? And to do that, we use these two pieces of information. We call it stuckness predicate and truncated predicate. So together they form something called discriminating predicate for the node F7 which we are exploring. And the synthesizer does two checks at this particular point to find out whether they are equivalent in some sense. The first check is checking whether the stuckness predicate implies the strongest force condition you will reach at this particular. If you take this path, the strongest force condition is implied by the stuckness predicate. So what this is doing is that if you don't have any truncated paths, and it was all kind of finite, and then this particular check is sufficient to imply that if there was no solution under F7, you're not going to get any solution under F9. So this is just checking whether if there is any choice here was also possible over here. So this is only partial thing. You also have to make sure that if you avoid taking F9, you are not going to miss any solution which are possible under F7 and which are truncated. To do that, you look into the vicinity of F5. So remember, you're making a decision at this particular point, and you try to see whether there is a node such that the push condition along that particular node, and this vicinity could be F5 itself, if the strongest force condition implies the truncated predicate. Basically, what we are saying is that if there is a path under F9 which can take you the solution which was truncated under F7, then there also exists a smaller path under F5 which can take you to the solution. Because what we're saying is that these are all the formulas which were truncated, terms which are truncated, and I can make further progress with it. As it turns out, these two pieces of information, these two checks, are equivalent, sufficient to prove that if there wasn't a solution in F7, there won't be a solution in the F9. You can put, it says that if there wasn't a solution in the F7, then you can avoid exploring F9 without loss of completeness of the synthesizer for a given value K. So, yeah, so this is the soundness theorem is straightforward in this case because it's coming from the types of etc. But the completeness argument is involved. What we're saying is that for all values K in given context and the libraries and the query, gamma, sigma, and type environment library in the query, if COBOL fails to find a solution, then there exists no solution of size less than or equal to K such that it satisfies the given specification. And the intuition for the proof is that the only place of incompleteness, so forward enumeration and is doing the only place it's avoiding some of the exploration is when it's avoiding this capable model struct nodes. And we prove that by doing so, we are both these conditions on both these checks allow you to prove that if there was a solution on the original condition, there exists a solution.
So that's one quick question. Sorry. So these completeness and soundness proofs properties, they did not hold for previous synthesis tools. Is this the first tool which has this property?
No, it's not like that. Most of the synthesizers from the deductive synthesis world, they didn't prove their soundness and completeness.
They will have soundness.
Yeah.
And the contribution here is in what exactly? As in like
no, so the thing is that they never looked into the effectual semantics and we argue that in the effectual semantics, even the soundness is broken and the completeness. If you're just doing an enumeration in the forward direction, and if you're enumerating everything, your soundness, your completeness is not broken. So I think the better way to answer that question, most of these proofs of soundness or completeness are very specific to the algorithm they have in the paper, even for us. So it's not straightforward to say whether their proof of completeness holds in this particular setting, but their soundness proof does not hold in this particular setting for.
And the setting being the
effectual libraries. Yeah. So I think if you ask me, novelty is the effectual setting, and in order to handle that setting, you have to do all this CDCL and other stuff. If you remove this, as shown in the empirical results as well, for kind of time bounds of 5 minutes and even 10 minutes, many of the tools will find a solution very easily. So I think so. Yeah, so there are just two questions at this particular point about the evaluation of these things. So remember, we need two things for evaluation. We need libraries which have specifications, factual specifications, and we need these interesting queries. And so for getting libraries for effectual specification, we went into looking for various effectual libraries that people have tried to verify. And vocal for OpenML was one. This is for vocal, look into their project. And there are these database transactions in Popul 11 paper, which are defined as libraries, and then we are trying to verify property of this. So we looked into some of the other verification works where we have verified libraries and used their specifications as an input to our specification. And it was easy to do that because full type is the standard way of giving those specifications. So it's most of the time it was writing usage translated into our maybe a different dialectic languages. So, but the query is interesting because how do we come up with interesting queries? So what we did is we used this idea that synthesis and verification is dual. So if somebody has asked whether this database transaction satisfies a given property, we reverse the query. We say that given this specification, can you come up with a database transaction and given the library and the specification, can you come up with a database transaction which satisfies this particular specification? So we just use that idea to take the original query of verification and translate it to synthesis. In some of the cases, we couldn't do that, particularly in the graphs and other kind of things, but in many of the cases, we could. So, in the view of the time, what I will do is I'll very quickly summarize this particular thing. So, what we found is that if you look into details of, so there are multiple such graphs in the paper, but each graph has 4 different bars. And overall, this is the time of forward. This is the time of that is forward plus backward plus the CDCL. Right is the time when you don't have backward. So the idea that what happens if we remove the backward, how does the forward plus the CDCL behave? This is showing this. And this is time on the logarithmic scale in seconds. And the black bar, which is missing in these cases, is just the backward removing the forward and the CDCL. So this is answering the question whether backward is able to find a solution in a given time. And all these experiments are done in time limits of 5 minutes. If I remember correctly. And finally, the green bar is just the forward synthesis without any backward, without any CDCL. So the difference between this and this is showing the gain by having a CDCL version. And the difference between this is showing how much backward is aiding the synthesizing. And we found that in most of the cases, backward alone was not able to find And along the x-axis, we give the size in terms of like what are the efforts against the result. We give the size of the program in terms of the ST nodes and the size of the specification. So one of the limitations in the synthesis world is that we are able to synthesize very small programs, and this is in the same ballpark as any other. Our future work solve this, we are able to synthesize double and triple size programs, which is under submission. So the backward synthesis couldn't find solution in most of the cases, but the difference between these and these shows that even though it couldn't find a solution in itself, it does help in many of the cases. So we also found that without CDCL, if we remove the CDCL, the synthesizer performs very bad. Finally, we found that in some of the cases, only cohort was able to find a solution. And especially when you are trying to add more and more elements in your table, or trying to synthesize larger and larger programs, backward and forward together are good. So I think, and then there are certain cases where backward was able to find a solution in some cases. And Q was a good example of this because we found that in case of Qs, there was some of the specifications of the Qs on the vocal library were very precise. So as you have more precise specifications and you are synthesizing small programs, I think this did happen. Okay, so I think I'll complete this. At this very particular point, how much time I have left? Maybe around 5 minutes. 5 minutes? Okay. At this particular point, I do want to talk about coverage verification work as well. So I think this is interesting because it got some recognition at PLEI recently, and this is also a work where I work very closely with the student. So formulation of the problem and other things were done with the I and Z, and then the installation also they were writing all the time. So the idea of the thing I want to convey is that coverage verification is a bit distinct problem, and safety verification, now understand we have this output space and safety specification. And the question we are asking is that every output generated by the program is well within this space. So this is unsafe, rather this is safe. This people will understand, I suppose. So the coverage verification question is the dual of this question. What it is asking is that given the coverage specifications, again carving out the space in the overall output space, the program generates all possible outputs or not. So this particular case where although every value generated by program output is included in, does satisfy 5, but still is unsafe because there are place values which this program cannot generate. And rather, this particular thing is a safe coverage with respect to the coverage verification question if you are trying to do that. So more recently, there has been some interest into trying to prove this kind of coverage verification properties using incorrectness logic, which is a variant of full logic for verifying approximate properties as I have mentioned here. So the question we ask is that there is a very well understood idea of automated verification. So we are interested in automated verification for the safety correctness question, which is that if you have a safety correctness argument, you have a core approximation of this style specification, you have a system called as refinement types, which can verify this in an automated fashion. So the question, and this refinement type is based on the underlying principles from the whole logic, if you want to compare with the physiological work. So we ask the question, in this particular work, we ask the question, what will be an analogous automated verification system for the coverage correctness question? And we call this thing coverage type, which looks awfully equivalent to this. So the interesting thing to note here is that this coverage types allows you to reason about coverage properties, while refinement allows you to reason about safety property. So I think what I'll do is, I won't go into this. I think I know I would have talked about this. So I'll give a very brief one-to-one example of how it differs, how this makes the whole type system differ. So on the first axis, we can there are terms in the language. So let's say you have literal in the language, you have non-deterministic choice, a natural number generating function, which is a function. And on the second row, there are these values. If you have a notation semantics into the set language, these are the values these could be reduced to. Why this language? If you read the paper, you'll find out, since we are looking at test input generator, this was a useful language to have. So, but if you just look at And I won't go into all the examples, but if you just look at this particular term now, if this is your term and you give a refinement type like this, what you're asking is whether every value this term reduces to satisfies this specification, which is true, because what you're saying is that every value this one will reduce to will always be equal to 1. And the cover type also asks the other question saying that does u is equal to 1, every value where this is true is generated by this. In this particular case, it does. However, if you look at this particular case, here you're saying that I'm looking for all the values, I'm looking for a term which reduces to all the values generating mu is equal to 1 or mu is equal to 2, then this particular term does not type check. Rather than in the over-approximate world, it does type check because all you're saying is that the value 1 reduces either to 1 or reduces either to 2. So as you can see, what happens is that I'm going to summarize this. But what happens is there is natural underlying denotation semantics into the set. So all these programs have reduced to either 1 or 2, or natural numbers or integers. And in the refinement type world, in the coverage type world, the subtyping check, what is happening is contravariant with respect to the subset relation in this set world. While in the refinement type world, these are covariant. I won't go into covariant and contravariant again, but they are covariant with respect to the subset relation. So basically, in the coverage type, you're asking that every value produced you're asking that every value is produced by. So you're asking that every value where this particular condition is true is produced by the term. In the refinement type, you're asking that every value produced satisfies the given constraint. So again, I encourage you to read this paper as well, where we apply these ideas to coverage verification of property-based testing and testing to generate this. So I think this will be the last leg. I take maybe 5 more minutes, if that will be.
Sure, that's
Okay. So I think I will summarize everything in one slide. I won't go into out of this. So moving forward, there are multiple directions the future work is taking us, and one direction is that we are trying to push this fundamental contribution in this verification. When I say fundamental contribution, I mean that we are trying to see what are the cases which are not with the current state of the art is not able to handle in synthesis as well as verification, and add a more formal kind of systems to handle that. And one good problem in that world is the synthesis in smart spaces. And earlier somebody asked, like, what happens if you keep on refining the queries from the user? As you keep on refining the queries from the user, the search space becomes sparser and sparser. Intuitively, it should be that as the user gets more information, the synthesizer task will become easier. But as it turns out, as we get more information, the synthesizer has to filter out a lot more paths, and that's why your search space becomes very sparse. And here we use the idea of taking cues from model checking world. We are trying to see whether while doing the enumeration, can we find similarities between terms and reduce them early on. And without going into all the details of this, the general idea is that you want to do similarity reduction, and tree automata are a good way of kind of representing this overall space of terms you are enumerating and doing similarity reduction. We introduced this notion of called as qualified tree automata. And the idea is to, and I can talk about this offline if you're interested, the idea is to embed refinement types as node of tree automata. Once you can do that, then it allows you to represent this whole space of libraries and the terms you are using, you are generating using those specification, using tree automation. And then the subtyping becomes a similarity, and you can collapse these tree automation early on while you do the enumeration process. Then there are other direct application of synthesis to coverage typing. We are looking into how we can use this under approximate reasoning for synthesis. We are also looking in applying synthesis to novel domains. So this is a work with another student where we are trying to synthesize designs in the robotics world given the user query. And we find that the symbolic approaches don't stay for most of the things in the robotics world, because the search space now is, if you're looking at the search problem, the search space is very big, because along with each design, you're also designing control policies if you're aware of the robotics synthesis world. But the idea is that the search space is much bigger, and alone these kind of deductive synthesis techniques don't work, so you have to use some kind of neural techniques to do approximations at various places in order to reach to precision. And then there has been some application into the industry, which I was not totally aware of, but some of the people in the industry, like thesis research and IB research in software, they are interested in applying synthesis to data format transformations. The idea is that we have data in one form and function manipulating that data. We change the data format, how do we change the functions which are manipulating them in order to take account of the changes in the data format. So I think there are some wonderful courses at TFR which are new. Actually, I did find them at other places. Mathematical logic was not taught in many other places, and I think programs and tools is wonderful. But I think I will just this slide is okay. I think most recently what I did was some kind of organizing special interest groups. But as future, I want to. I think there were questions about this. I want to float courses which are more targeted towards logical foundations and software correctness. Software foundations is one good example of that. And I also want to push for courses which are more closer to principles of programming languages, etc. And then, yeah, definitely there are organizations that are going to be approved. So, yeah. All this work was done with a lot of effort with a lot of people. So I should be able to this here. Thank you for listening to the talk. And yeah, many of the things which we have questions you can check document.
Questions? Okay, so then maybe we can take the questions. Okay, and so he's sitting in the visitors room, so if someone wants to meet him, yeah, he's here also tomorrow. Visiting. Okay, thank you. Thank you. Stop.